Hi guys, welcome to my channel. I know it's been a while since the last video, had to do some stuff for school, but I'm back again. I hope you had a great year, and this episode is going to be a special one. Actually, it's going to be the start of a new series called Science Peaks. And what I'll be doing there is I'll answer interesting science questions that you may have in a short amount of time. So hopefully this won't be longer than a couple of minutes. Today I'll answer the question why most of the space stations in science fiction movies rotate. Now this has got something to do with the equivalence principle, which I'll talk about later. So let's start. Are you excited? Great, because I'm too. The first thing we have to clarify is the difference between speed and velocity. You may think they're the same, but they're not. You see, we use the word speed in an often scalar context. Just say you're driving with a car and just saying I'm driving with 30 miles per hour. So it's got a specific value, but it doesn't have a direction. That's where the velocity comes in. Velocity is similar to speed, it's also scalar, but it's also vectorial, which means it's directional. A driver doesn't only want to know his speed, he also wants to know where he'll go, and that's the vector. So now that we've clarified this, let's turn to acceleration. Acceleration is basically the difference in velocity divided by the time. I guess you know this, but here comes the point. Think of the moon orbiting Earth. As time passes, the moon makes a circular movement around Earth. But does it accelerate or not? This is exactly the point, because the speed always stays constant of the moon, but at the same time the velocity doesn't. And the reason why being that the velocity is vectorial. And if you look at the vectors of a circular motion, you'll see that they change constantly. And that's the point. So the speed stays the same, but the velocity changes. And the difference in velocity is acceleration. So now we know that the moon accelerates. But what's that got to do with rotating space stations? In Einstein's general theory of relativity, there's an effect called the equivalence principle. The equivalence principle basically says that gravity and acceleration are the same. Think of a rocket flying through space. A person inside the rocket feels being pressed into his seat while the rocket accelerates. Now look at the same rocket and the person sitting on Earth. The man also feels being pressed into his seat, but that's normal because that's gravity. So we're starting to get the point. It's the same. A person inside the rocket cannot tell if he's really accelerating or being pulled down by gravity. Now let's come back to the space station. As we've learned, the people inside the space station are being constantly accelerated, which means that they feel the force of gravity. But why is all this important? You see, during long duration flights, the human body alters differently than on Earth. And this is a major problem as the bone mass decreases, which means you get shorter. And in weightlessness, the muscles don't have to work against the force of gravity, which means that they get weaker. But these are only a few examples. There are tons and tons of problems that occur in zero gravity, which means on a long duration flight, it's a lot better to simulate gravity through this rotating movement of the spacecraft. Astronauts on board the ISS don't have this option, which means that they constantly have to exercise in order to keep the problems of zero-G as low as possible. That was it guys, I hope you found this topic interesting. If you liked this video, please give it a big thumbs up. Also, if you have interesting questions you want to get answered, just write them in the comments below.